to talk about approximations of cumulant distribution functions. We have put here saddlepoint approximations, but we are talking about something actually more general than that. We are going to see that saddlepoint approximations are indeed the special case of this work. That is done jointly with Daja Anad, Jean-Marie Gorce, and Philippe Paris, who are here. All right. So there is a mistake. The date is wrong, but the rest of the slides are correct. All right. So the motivation is deeply rooted in wireless communication. So we essentially have a source that has M symbols to transmit, right? And for each of these symbols, the transmitter chooses a code word of length n that we see here. Let me see. And then when we put that code word to the input of the channel, then we obtain a vector with a given probability that we use at the receiver to guess what the output of the source was. So the memoryless assumption, right, that we have is essentially that given an input, the probability measure of the channel is a product measure. And the idea that has been turning around that of a code is essentially an M lambda code, which is represented by a set of pairs. One that is the code word that we are going to use, and that D, which is the decoding set. Essentially, when the output of the channel falls within a given D, well, we assume that the symbol that has been transmitted is the corresponding index, right? So of course, these decoding sets are disjoint, and the union we expect is the whole space where we expect the output of the channel to be. These arrangements allows us to define the average decoding error probability, right, which is 1 over m, the sum that given that the input of the channel is ui, well, we are outside the decoding set of that index, right? So if that is smaller than lambda, then we said that we have an nm lambda code. All right. So the question that is very interesting here is what is the minimum of that lambda given a pair n and m, right? So this is what we define as the minimum average decoding error probability. And there are a number of results that provide lower bounds and upper bounds on that. So this one in particularly is given in terms of this function t, right? That we have. So the upper bound has some optimization to do, so does the lower bound. But the important point here is this function t that I would like us to see, which is the sum of two probabilities, right? So one here and another here. So that can be written as expectations, right? And the key point that we are going to use is the fact that at the end, these are Lebesgue integrals with a given, with a very particular measure. So this is essentially the point that we are going to be using, all right? Another key point is the fact that those probabilities are given in terms of this function iota tilde, right? That is the logarithm of a radon-Nicolin derivative, right? That has the channel therein and a given measure Q that is a parameter of the calculations. So there are no more assumptions in the following other than the fact that the channel is going to be a product measure, and under that we essentially have that this tilde iota is the sum of other functions, right? That are IID random variables. So this is the key observation that I want to make. At the end, the calculation of that t, which is an expression that is difficult to calculate, turns out to be given in terms of sums of IID random variables. Okay, so the phase, let's say, of the expressions is not interesting here. What is interesting is the fact that at the end, that calculation depends essentially over sums of IID random variables. Okay, so
why should the Nicolin derivative exist? And so I don't say this is for, you say it's for all measure QY.
Exactly, for all measures.
You're given the curve, which is the channel, right?
Yes.
And so
Q,
I don't understand what why should this Nicolin derivative exist?
Okay, so the channel is given to us.
Yeah.
Okay, so this is something I cannot choose. On the contrary, Q is something we choose in the problem. So Q is a parameter that we are choosing here exactly.
So for all things such that
exactly
the radon
derivative exists,
then you define this T function and
exactly.
Sorry.
Exactly. All right, so these bounds are difficult to calculate because even if we have sums of IID random variables, the calculation of the CDF is complicated, and this work has been driven by the Bernoulli type theorems that are essentially the main mathematical tool to obtain the bounds that we have been seen in the previous presentations. Key good thing of the Bernoulli type theorems is that we have an approximation, right? And at the same time, we have lower and upper bounds on the error of that approximation. So this is something that is very good for our calculation. The problem is that the upper and lower bounds are very loose, and this is very problematic. On the other hand, saddle point approximations, that are other type of approximations, are known to be very good, right? But we don't know exactly the error that is induced when we approximate the sums by the corresponding saddle point approximation. So the objective of the presentation is essentially to characterize that error, to provide the upper bounds and lower bounds on the error. All right. Perfect. So this was the motivation. Let's see now enter to the core of the presentation. This is indeed very simple. So stop me if there is something that is not clear, because it's my fault. Probably I'm not explaining well. Let's consider n independent random vectors. So y1 up to yn. All right. And let's assume that they all follow they all induce the probability measure py, right, in this measurable set. And then the cumulant generating function, which is going to be a key element here, is going to be denoted by ky. All right. So the sum is going to follow this. This is going to induce the measure pxn, right? And the cumulative distribution function is going to be denoted by fxn. So is this precisely the fxn that we want to approximate? And we are going to call that approximation by the tilde fxn. All right. So the type of result that we are seeking is upper bounding the difference that we see here. All right. So first, which is the explicit expression of this f hat, right? And another one is the upper bound on this difference. All right. So this is the objective of the presentation. All right. So we are going to define this set of vectors of dimension k, for which the cumulant generating function qy is finite. All right. So this is a set that is going to be very important for us. And then we are going to define random variables that are tilted with respect to py, and we are going to denote these random variables by y1, 2 up to n, with this parenthesis theta on the top. And what is the meaning of that? Well, the Radon-Nikodym derivative of py theta with respect to py has this expression here, all right, where this is essentially a product, right, theta transpose y, and this is the cumulant. All right, this is the main assumption, and this is in literature it is known as Escher tilting. All right. In case you are wondering yourself, why are we doing this, I want to make a connection that I find very interesting, is the fact that py theta is the solution to that optimization problem that we see there. All right. So the first term is an expectation of the product theta transpose times y, and then we have a sort of regularization, which is the relative entropy, Kullback-Leibler, between p, which is the dummy variable, so it's the measure that we are optimizing, and py, which is the reference. So the solution to that problem is exactly the definition of Escher tilting. All right. Now, many questions may appear here, right? So we can, for instance, find. Okay, so I'm going to say everything we haven't done, right? So that we that we identify all the degrees of freedoms for improving this result. Okay, here in the general formulation of this type of problems, we may find, for instance, a function f that takes us as argument theta and y. Here we have assumed that f is simply a linear function. All right. We often find also a lambda, right, as a parameter that traits the importance of the regularization and the first term, right? Here is equal to 1. The fact that it is equal to 1 here appears very, very natural because that can be included inside theta, okay? So that doesn't make a much difference. And on the other hand, we have chosen KL as a regularization. All right. So many open questions of why we have done all these things. The lambda part we can answer right now, so it is not important because, as I said, it can be inside theta. The fact that this is linear, right, is something that we're going to see in the next slide. And then why we have chosen PY as a reference? Well, it is because we know it. This is an assumption of the problem, but we may have chosen another reference for the problem, right? Okay. So
can I ask a question?
Yes.
So I mean, you have this first optimization problem.
Yes.
And then you give a solution in terms of KY, but what's the connection between the first? I mean, I don't see KY in the. I'm missing something.
Yep. Exactly. This is the log partition function. Actually, the ky, which is the cumulant generating function, in this problem becomes the log partition function as well. Okay. Exactly. So this is. I mean, I wanted to show this because there are many interesting connections with things that we know and this Escher tilting. So one of those is exactly the key role of this function ky that plays this dual role, cumulant and log partition function. If you, I mean, independently of this problem, if you want to know properties of this problem, there are these two reports there that include all these properties, including this one there. Okay, so with this in mind, okay, if there is a slide that is important in this talk, is this one. So let's do it slowly together, so that we get the main idea. Because I mean, more important than the result, I believe that the method that we use to get this is actually more important. So we start with the set, right? A that for which we want to calculate the measure with respect to the sum. So remember, xn is the random variable of the sum of all the y's that we have. Okay, so just by transporting through the xn equal y1 plus y2 up to yn, we can express this measure in terms of this expectation with respect to this product measures here, right? And then here is the point at which we use the Radon-Nikodym derivative for changing the measure. So we are calculating the expectation or the integral with respect to this product measure, right? And now we express it as the product of these measures y1, y2, okay? And then we obtain this expression, right? We have an explicit expression for this Radon-Nikodym derivative. So it becomes this exponential term, right? And what is interesting here is that we now see some of the random variables, of the new random variables, of the tilted random variables here, and the sum here. Okay, so why is it important? It is important because it allows us to define another random variable, which is the sum of the tilted random variables. So this is what we obtain, what we see here, right? Again, and then the expectation is in terms of that new sum of random variables, okay? Now, I was telling you why we didn't choose another f other than a linear function is because we would have not obtained this summation here otherwise, okay? Why did we choose py as the reference measure? Well, it's because I mean, we could have chosen something else, but we would have gotten another Radon-Nikodym derivative here, okay? So we are assuming in this case that this is equal to 1. Okay, so we obtain now this other random variable, which is sum of tilted independent random variables. Okay, so we started with a problem that was already difficult, and then I am showing you an expression that is even more difficult. So why are we doing this? Well, we have gained here the freedom to choose theta as we want. If you put theta equal to 0, you go back to the original problem. Now, how are we going to choose theta such that it is something useful for us? Well, if we go in this direction, I mean, trying to use this expression as is, we are not going to do better than the problem we had at the beginning. Something we can do, and that is different, is to approximate theta by a Gaussian random vector. Okay, we could have done that at the beginning, right? But this is what everybody was doing at the time. So that is the Gaussian approximation. So here we are not approximating the original sum, but the sum of tilted random variables, okay, for which we have theta to work out. All right. So it turns out that if we treat Sn theta as a Gaussian random vector with the same mean and same variance of the original one, right? Then we obtain this expression here, okay, which is what we call a exponentially tilted Gaussian approximation of Pxn. All right, and this is going to be very useful. We will see. I want to make a parenthesis here to show that if we choose a Gaussian measure, right, with a given mean and a given variance here, so this K1 and K2 are the first and second derivatives of the cumulant generating function. So necessarily those are means and variances, okay? And we obtain this expression here. So essentially we have a Gaussian measure, right, multiplied by an exponential term. So this is what allows us to say that this is a tilted measure. All right, great. And then, as I said, this first derivative and second derivative has to do with the mean vector and the covariance matrix. All right, so with this at hand, we have the first result. We have that the absolute difference between the measure of the set A and the approximation that we call eta is upper bounded by this exponential term times something that is very familiar to us, because in the Gaussian approximation, Bernoulli type theorems, we obtain already this bound. So this already tells us to speculate that if the argument of the exponential function is negative, we are already doing better than the Bernoulli type approximation, which is actually very good news. Now, in the dimension 1, the choice of theta is very simple. Here we have to, given that there are many dimensions, we need to arrange the choice that we make of the coefficient that we have for theta, and then we come up with this function a that is written there. Not necessarily the optimal choice. We don't have a proof of optimality, but it turns out that is a very good choice. All right. This term here has to do with the third moment that is a constraint that appears also in the Bernoulli type theorems, and then implies that the random variable y has to have a finite third moment for this to make sense. All right. So what we promise is an approximation of the CDF, and so far we have shown an approximation of the measure. So how does this connects? Suppose that we want to evaluate the CDF at this point vector x, right? So what we do is that we construct a set that we call here AX, that is essentially the product of intervals of the form -infinity up to x1, Cartesian product -infinity x2, so on and so on. And then there is this equality between the CDF at x and the value of the measure. For free, then we get a result that tells us that we can approximate fxn, right, by our eta that we have found already, and then the upper bound remains the same. Now, big point is, how do we choose theta? So there is theta all over the place. So on the left hand side, theta is inside eta, right? is in the argument of the exponential function and is already here in this function that represents the third moment. So the optimization already in the right-hand side is going to be difficult. So what we do is, let's do something suboptimal. Let's try to optimize theta to minimize the exponential term. All right. So if we do that, essentially we need to solve this problem here. The cumulant generating function is infinitely many times differentiable. And then there is no problem. Actually, this has all the beautiful properties, unique solution, everything we want. All right. A warning here is that for some values of x, right, for a particular set of points at which we may approximate f, theta is going to be 0. And we know that if theta is equal to 0, we will end up with an approximation that is as good as Bernoulli type approximations, right? So the key point is how to make it, how to calculate then the approximations in those points for which all thetas are 0. All right. So here, intuitively, what we are saying is that the problem appears when all the components of the point x are bigger or equal than the mean of the true random variable xn. Okay. So this is the case. So this is our vector x. Ax is the vector. The blue is the set that we calculate to calculate the CDF, right? And then when we are in this situation, well, what we say is, let us not approximate AX, let's approximate the other sets, the yellow and the gray. Okay, so that is the choice that we make there. And then we end up with this approximation of the CDF. When we are not in the situation in which all components of theta are 0, well, we go with eta, and then we indeed approximate the AX, so directly the CDF at that point. Otherwise, if some of the components of theta are not 0, then are not all 0, we approximate instead of approximating AX, we approximate the yellow and gray sets, right? And then we have this expression for delta that is not different from the one we have seen before. And then theorem 4 is the big result, right? We have now an approximation of the CDF, which is this z, upper bounded by delta, okay, which is what we promised that we were going to deliver. Immediately we obtain an upper bound and a lower bound for the CDF at that point, right? And we immediately see that for some points at which we want to approximate f, this approximation is exactly the saddle point approximation. All right. We didn't seek for approximating the saddle point approximation. We did actually many things that were suboptimal, and still we find the saddle point approximation as a special case. All right. Okay, so that was a good point. Then in the scalar case, we have something very simple, right? Because this a function is either choosing if we have an interval, either we choose the smallest value or the biggest value. And the key point is that it highlights a property of the solution. So the point at which we want to approximate the CDF x minus the mean of the ground truth random variable times the optimal theta, so the one that minimizes the exponential term, is always positive. So that's why sometimes we have to choose to the right of the mean or to the left of the mean. Okay, so that explains that choice that we have to make at the beginning. So these are the shape, let's say, of the previous expressions that we show for the scalar case. Let's go to the examples. So here we have 100 Bernoulli random variables with parameter p equals 0,2, right? And we have calculated this CDF numerical. Okay, so the computer can do that very easily. And then we put on top of it the Gaussian approximation. Okay, and we see that it fits actually relatively good. If we go to the precision that Jean-Marie was talking about concerning 10 to the power minus 9, we see indeed that the Gaussian approximation doesn't provide us such error for us to talk about this type of reliabilities. Okay, if we put on top of it the approximation that we just derived, we see that it has actually a better performance, even in those points close to I mean, very far from the mean. So the tail, what you see there here is essentially the tail here that we see with the zoom there. All right. If we put on top of it now the lower and upper bound that we obtain from Bernoulli type theorems, this is what you see there in blue, right? Relatively good around the mean, but very bad upper bounds and lower bounds when we are far away from the mean. Okay. Now the good and bad news at the same time. So we see that our upper bounds and lower bounds, so the red ones, are extremely good far away from the mean, but actually we are not better than the Bernoulli type upper bound and lower bound, right? So there is a regime at which we recommend to use Bernoulli type theorem, so very close to the mean. But when you are far away from the mean, this actually works fantastically well. Meaning you have an upper bound that is already extremely close to the approximation, right? And this becomes more flagrant in the vector case. So in the vector case, Bernoulli type approximations are even worse, right? So here what is interesting is that if we, for instance, construct these vectors, that is two-dimensional vectors, a very simple example here, right? So you take two Bernoullis and then you construct a vector y using this matrix, right? And then the plot is the following. The plot is the CDF evaluated at a given point x. And how do we construct that x? Well, we take the mean of the sum. We take a direction, a vector d, right? And a scalar a. So we are going to change the value of a so that we get away of the mean, right? Through that direction vector. And then what we see is that the behavior is of the Saddlepoint approximation and the Gaussian approximation when a is equal to 0, so exactly in the mean, the approximation is good. The Gaussian approximation becomes extremely bad, right? Far away from the mean, whereas the approximation that we have shown is actually a very good approximation, and so is the upper bound. So this is essentially the crazy result that we want to highlight. All right. So contributions for taking this very easy upper bounds and lower bounds on an approximation of a CDF, right? That does some very good far away from the mean, which are the points of interest for what we were talking this morning. Special cases of this bound is the Gaussian when theta is equal to 0. Saddlepoint approximation when theta is chosen to minimize the exponential term, right? And then back to the motivation, we can now evaluate this function t that I showed you at the beginning, right? Using this result. So for a very simple example, a discrete channel that we see here on the left. We plot the Gaussian approximation, right? The blue one here. We see that the true, I mean, in this case, it is easy to calculate. So the black curve is actually the true value, and the Saddlepoint approximation are exactly the same. All right. The bound for this case, due to the Gaussian approximation, is extremely bad, right? And when you put there the upper bound due to Saddlepoint, you see that it actually is a very tight upper bound. So is the lower bound. And at a given point of time, you see that the Gaussian approximation is even outside that interval between the lower bound and the upper bound of this work. All right. Okay. So Laurent was talking about the alpha stable. So we have a simulation here. So Z, the noise is now alpha stable, and for that type of noise, you cannot calculate that T easily, but then you can actually approximate it. So you see there the Saddlepoint approximation and the Gaussian approximation. Yep.
Since you have this Gaussian approximation, you have moment requirements, right?
True.
And so how does it fit with the Laurent case where the alpha stable would have no moments of so how I'm not sure to understand how the two things can be connected.
Okay, just let me think about it. So the given an input, the channel is going to be an alpha stable, right? Z I, right? Exactly, it's additive.
It was additive.
Yeah, is that additive?
And,
Exactly.
Alpha stable, therefore no
Exactly.
no second moment.
Yeah. Yeah.
Depending on alpha. And therefore, I mean, but it seems that in your setting, when you are adding, you are looking at the sum of these random variables.
True.
Assuming moment things so that you could work out some central limit theorem for partitive version, something like that.
Yes.
But there were moment conditions for the which were lying there.
Cumulative generating functions.
No, the cumulant is the cumulant function.
The second moment is
No, the cumulant generating functions. Yeah, we always have a cumulant. We always have a CDF that always exists.
yeah,
The CDF exists, and the so the CDF exists, and we are approximating the CDF, right? And we require that the theta at which we are evaluating this has a finite cumulant. That are the two conditions that we require, right? Okay, but I mean we can look at the paper together. This is I have all the doubts now.
excuse me, but like a question here would be
Yep.
when you do exponential tilting of the distribution. If the distribution is Gaussian, the exponential tilted is
Gaussian.
Still Gaussian. So you're approximating your stable with Gaussian. Non-zero mean Gaussian.
No, the mean varies a lot, and that is the whole idea.
You can change the mean of the Gaussian.
And the variance. So the
covariance.
Yes, exactly.
But you remain. So I don't understand how you can have a good fit of the tail of the distribution of a stable distribution with something that at the end is Gaussian.
So we are changing both, eh? We are changing the mean and the variance.
Yeah, but the tail
and
is
then
fundamentally different for a stable distribution.
Let's see the bounds. Let's see the bounds, because we say that there are intervals within which we are going to find it, and what we see here is that there is an order of magnitude difference. So that may be
perhaps we can continue the discussion after the talk.
Okay.
But I think it's a good point.
It's a good point. Yeah, alpha stables are spidery things. So
he's not here, but
yeah. So essentially to wrap up, we have the upper bounds and the lower bounds, right? And the applications that motivated this work were essentially the calculations of these upper bounds that we obtained from the work of Yuri, right? And this is that what we have provided. Thank you very much.
You have 7 minutes, so we can go back to the discussion.
To the
Show that. It explains the previous slide. What is the x and y axis?
What is the x and so this is the function t. So I would have loved to so this is the function t that we see at the beginning of the presentation. So what we are plotting here is the function t, the sum of these two probabilities. Am I because I didn't do the simulation, so this is our student simulation. So
it's just
Philip,
probability
is the lambda, yeah, so it's the sum of
with n. It's error probability computed on the alpha stable channel.
Okay.
Maybe just an element of discussion. Like you said, it's with the change of measure, we move finally the Gaussian approximation to the plane. So we still do an error approximating the distribution by that, but the error down is bounded. The bound is lower than the one that is given by the variation approach. It's the error on the approximation of the measure that is less at this block length and at this error rate than the Gaussian approach without the change of the measure, actually.
Yeah.
Why would you use edge-without extension?
We can, and we would have obtained not something better than this. Yeah, true. That's a way to go, indeed. That's a way to go.
Because with edge extension, we can control explicitly the error between the two distributions. And I think in your approach, you have no theoretical bound between your original distribution.
Yeah. So if we take the edgeworth expansion, there is something we can factorize, right? And then we will have the 1 over, I mean the series of terms. What we can factorize in that series is exactly the Saddlepoint approximation. So, and what we are approximating, I mean, we ended up approximating was exactly that term. I pointed out many things that we chose in this work, right? Because it was easy to calculate, right? But there are many choices that may be done differently and obtain better approximations. That is a truth, right? Now, obtaining a lower bound that is so close, right? Less than I mean, several times, several powers better than the Gaussian was already very good for that, and then we stopped there. But I agree with you. There are many things that we can choose here differently that will lead us to a better approximation. I don't know how easy to compute, but certainly better. Yeah. For instance, choosing another reference measure other than PY certainly is going to give us something better, and we obtain now theta and the reference measure to optimize in this work. Yeah.
Could you say a few words on the? So I understand that it's a fixed n, but I'm trying to figure out the connection with large deviation theory. What's the connection between the Saddlepoint? You try to. You have the exponent. You try to find some thing that is negative, and so I mean, could you say a few words? I understand it's way better, way more precise.
Yes, because it's not asymptotic, exactly.
It's for given n.
Mm-hmm.
But I mean, so assume there is large division principle for your IID random variables. What's the connection between that and the rate function of the large division principle?
Okay, so let me show you the expression, and we will see. Something interesting is that in this result we have two things. We have the exponential term, right? That contains this expression inside that is the Saddlepoint approximation, and we obtain this square root of n, right? So let's consider this as a constant times the square root of n. So we have already a square root of n and exponential, right? So if we see how this difference actually scales, we have everything. We have the factor 1 square root over n may not be the one that we are expecting, and we have the exponential term that we have. So not even in the limit, even for finite n, we are a constant factor away from something optimal.